In this video, we introduce the idea of antiderivatives. So the definition is that we let f and g be functions. If f is the derivative of g, then g is said to be an antiderivative of f, or an indefinite integral of f. So let me give you a little bit of an explanation. Let's say that we've got the function g of x, and if we differentiate g of x, we get this new function f of x. So f of x is the derivative of g of x. Also, g of x is an antiderivative of f of x, or it's an indefinite integral of f of x. So when we're talking about antiderivatives, we're trying, if I give you a function and I ask you to find an antiderivative, what I'm asking you to do is find a function whose derivative is what I gave you. So I would give you f of x and you would have to find g of x. A more concrete example is that the derivative of 2x cubed is 6 times x squared. And so this is playing the role of g. The 2x cubed is playing the role of g, and the 6x squared is the f. So the derivative of g is f. The derivative of 2x cubed is 6x squared. An antiderivative of 6x squared is 2x cubed. Notice I'm saying an antiderivative and not the antiderivative. Is 2x cubed the only derivative of 6x squared? Are there any other functions that you could differentiate and get 6x squared? Well, how about 2x cubed plus 1? 2x cubed minus pi. When you differentiate these functions, you're still going to get 6x because these constants are going to go away. So actually, any function of the form (2x cubed plus c), where c is a real constant, is an antiderivative of 6x squared. Alright? And just as we call finding a derivative differentiating, we find calling an antiderivative integrating, because an antiderivative is also known as an indefinite integral. Alright? Fact, if g of x is an antiderivative of f of x, then g of x plus c, where c is any real number, is also an antiderivative of f of x, and that's what we just talked about. Alright, so let's talk about some notation. The antiderivative of f of x is denoted by this symbol. There's this sort of long S shape. That's called an integral symbol. And then the f of x, that's the function that you're integrating. That's called the integrand. And then the dx is just the differential of x. It's this integral symbol along with the dx that is the integration notation. This is telling, the dx is just telling you that you're integrating with respect to x, that you're supposed to treat x as the variable. And we will talk about the origin of this notation in a later section. So we need to talk about some integration rules. And essentially when you're integrating, you're just reversing differentiation. So we need to talk about how do you reverse a process that has many steps. For instance, what about putting on shoes and socks? In the morning, when you get dressed, you would probably put on socks, and then number 2, put on shoes, if you're doing something, say, fairly informal, or formal if you like. You put on socks and then you put on shoes in that order. But then when you come home in the evening and you remove your shoes and socks, you've got to undo the things you did previously, but in the reverse order. You'd have to take off the shoes before you take off the socks. So that's the idea here. We're going to look at these multi-step processes, and we're going to reverse the order of the steps, and we're going to undo each of those in the reverse order. So let's think about the power rule for derivatives. What do you do first? If you go from, say, 7, well, let's just say x cubed, you multiply by the exponent, and then you subtract 1 from the exponent. So when we integrate, we're going to want to do these in the opposite order, and we're going to undo them in the opposite order. So we're going to add 1 to the exponent, and then instead of multiplying by the new exponent, we're going to divide by that new exponent. So the antiderivative of x to the n becomes, well, we're going to add 1 to the power, x to the n plus 1, and then we're going to divide by that new power. So it's 1 over n plus 1. And then we throw on this plus c just to indicate that what we've actually got is an entire family of functions, and they all differ by constants being added or subtracted. Let's just say constants being added, because the constant could be negative. Now, this works as long as n is not equal to negative 1. I think if you can see that if n were equal to negative 1, you get 1 over 0, which isn't really going to be the answer we're looking for. So let's try some examples. In part A, we've got the integral of x dx, or the antiderivative of x dx. So I'm going to remind us all that that's x to the first dx. So we're going to find an antiderivative, a function whose derivative is x. So remember that what you want to do is add 1 to the power and then divide by the new power. So that would be x squared divided by 2. Don't forget the plus c. Of course, you can probably guess how you might check your answer. You should be able to differentiate this and get back to x. So if you differentiate x squared over 2 plus c, you are going to get x. Alright? How about x to the 6th? Integrate x to the 6th. Add 1 to the power, so it becomes 7, and then divide by the new power. X to the 7th over 7 plus c. And let's go on to part C. You've got the integral of 1 over x to the 4th dx. I'm going to zoom in so you can see it a little bit better, and I'm going to focus. Well, think about what you do if you're going to integrate it. You would first rewrite this as negative x to the negative 4, and then the answer would be x to the negative 3, because you're adding 1. Negative 4 plus 1 is negative 3. Divide by negative 3 plus c. And let me say a little bit about notation. This integral symbol, along with the dx, is the instruction to integrate. Once you've integrated, you want to get rid of that set of instructions. It's sort of like taking the square root of 25. Once you found the square root, you drop the radical symbol. Anyway, let's rewrite this as negative 1 over 3 x cubed plus c. Part D, we've got the cube root of x that we're integrating. So I'm hoping you're ahead of me, and we need to rewrite that as x to the 1/3. Add 1 to the power. So 1/3 plus 3/3 is 4/3, and we're going to divide by 4/3. Well, that's ugly. we can make it look a little better than that. Let's do that. Instead of dividing by 4/3, how about we multiply by the reciprocal 3/4? So this would be the same thing as 3/4 x to the 4/3 plus c. A second rule of integration is the sum and difference rule. You remember that when you differentiated, if you had a sum or difference, two or more terms added or subtracted, you could differentiate each term separately. The same goes for integrating. If you have the indefinite integral of two functions, you can find the indefinite integral of them separately. So in this case, we are asked to find the indefinite integral or antiderivative of x plus x cubed. So we can say, well, the antiderivative of x would be x squared over 2. We've already done that one. And then the x cubed would be x to the 4th over 4. Now what about the constant? Would you need a constant for this one and a constant for that one? Well, they're arbitrary, unspecified constants. And so if you had, say, a c here and a d here, those constants could be combined into a third function, e. But I'm not going to bother using an e. I'm going to go back and just use c. So really we just need a single constant. So let's look at our next example. We've got the integral of x plus x to the 4th over x cubed. You do not integrate the numerator and denominator separately. If you're asked to integrate this, you would not integrate them separately. So what can you do? Well, you can rewrite this. How about we write it as x over x cubed plus x to the 4th over x cubed. Now we can simplify that. This would be 1 over x squared, so that would be x to the minus 2, and this would be just x. And now we can use the power rule and the sum rule and get x to the minus 1 over minus 1 plus x squared over 2 plus c. And I'm going to rewrite that as negative 1 over x plus x squared over 2. If you feel strongly, you can find a common denominator and combine these into a single fraction. But I'm okay with leaving them like that for now. And as you might have guessed, this sum and difference rule can be generalized to any finite number of functions added or subtracted, or sometimes an infinite number of functions added or subtracted, but that's a topic for calculus 2.